Hi there, today's video is on gravitational field, one of the most confusing topics if you're starting this for the first time. It's not only confusing you, it has confused physicists over the years so much because it's invisible, it's mostly existent only when one of the mass is a celestial body is so huge. So it's very difficult to it was very difficult for the physicists to understand what could be the equations, what could be the fields that can govern this. So the first physicist who ever talked anything about it was Aryabhatta. He was in 5th, 6th century CE. He is the first one who said that the earth rotates around its own axis and somewhere hinted that there might be some underlying force. Then came a famous physicist Kepler after somebody named as Tycho Brahe. I'm not going into much detail here, but I just want to mention Kepler because Kepler's was the first person who ever came up with some relationship between the time around time of an orbit of a planet orbiting around the sun. So he was the first person who ever gave us any relationship. He said that the time period of rotation of any planet around the sun is proportional to. So this was a relation Kepler gave. He said that he came up with this relationship with a lot of data that he collected over the years. But the first actual formula or relationship came by Newton. Okay, of course, he is the god of classical physics. Okay, pardon me for saying god, but he's considered as one of the greatest figure as whenever we talk about gravitation. Now, what he said, he did some calculations, took the notes from Kepler, and he said that acceleration of a freely falling body because of some gravitational force is inversely proportional to the distance of the body from that surface. For example, if the body is on the surface of Earth, so let's say this is a distance from the center of Earth as r. So then the acceleration of this freely falling body, freely falling means there's no other force acting on it except the gravitational force. So the acceleration is inversely proportional to r squared. And of course, if a body has a mass m, it would be proportional to the mass. Okay, so then the force, so now because my force is ma, I'm just going to write it ma here. So obviously then my force is proportional to m over r squared. And if Newton's third law is also valid here, so if the force on this body is proportional to its mass and inversely proportional to r squared, this force should be also acting on the earth of mass capital M. Action and reaction are equal and opposite. So if this body A here is experiencing this force, then this earth here will also experience the same force. So then this force should also be proportional to the mass of earth, mass of the body, and r squared. This is how he came up with the formula for gravitational force. Now, then if you remove the proportionality sign, there should be some constant here, and that constant is gravitational constant. Okay, so what you need to know for your exams is this final equation. It is there in your equation sheets. You don't need to learn that, but you need to understand that formula. What does this shows? That the force is proportional to the product of the masses and inversely proportional to the square of the distance between them. I'm going to just show you this diagram on another page. Okay, so let's just see. So if I have two masses here, now I'm going to just see a capital M mass and a small m mass. If the distance between them is small r, then the gravitational force acting on each one of them is given by this equation given by Newton. G here so far is a universal constant. So if wherever you go in the universe, this capital G is going to be constant, and its value, again, you have the value in your equation sheet, so I'm just going to write it here. So 6.67 10 to the power minus 11 Newton meter square per kg squared. So that's the value of G. Don't need to learn again. What you need to understand is what's the direction. So this is attracted towards the small m, and the small m is also attracted towards the capital M. So because action and reaction equal and opposite, so both of them are going to experience equal force but in opposite direction. So that's it. That's your Newton's gravitational force. Now, when Newton was deriving this, he was trying to say that this entire Earth is a spherical body. Okay, that's a very bad sphere. So entire Earth is a spherical body. So this spherical body is assumed to be a point mass which is kept at the center of the body. So every spherical body, so if the spherical body has a radius r, it is replaced by, so this is capital M, it is replaced by a point mass, capital M, acting at its center, as its center of mass. So this is valid for every spherical body. So okay, let's see. If you see a football up close, it looks like a sphere. But if you see that football, if you keep your distance if you keep increasing your distance from the football, it will become smaller and smaller and smaller till it behaves like a point. So any sphere, anything which is spherical in shape, if you see it from a very far off distance, let's say you're standing here, this is going to behave like a point mass. So because the radius of the Earth is so large, we assume that it is acting like a point mass. That's it. You just need to know that a spherical body would behave like a point mass when the distances are very large. And now, of course, this Newton's law, so you'll see this word in some of the questions. That's why I've written it especially here. This is your Newton's. I'm going to use capital R here. So this is the Newton's second law. Sorry, not second law. Law of gravitation. Force here is directly proportional to the product of the masses. You can see here. And it is also inversely proportional to the square of the distance between the masses. See, again, I'm assuming that the bodies are point mass, their sizes are negligible, and the distance between them is r. So if I double the distance, because it is inversely proportional to r square, if I double the distance, the force would become 1/4. Let's do some more understanding in this. So if I have, let's just understand. Okay, I have the surface of my Earth, and then there is this famous Newton's apple. Okay, so imagine this is an apple. Now this apple has a mass of small m, and the mass of Earth is capital M. It acts at, this is the radius of Earth, and this is, let's say, height of the apple from the surface of Earth. So now the distance between the two objects is r plus h. Now whatever force acts on the apple, who's exerting that force on the apple is Earth. So it is downwards. The same force is going to act on the Earth upwards. The force is same. Why? Action and reaction equal and opposite. And what's the value of that force? That is nothing but G M first body, second body, divided by r square. You can calculate r from here. Now my question is, if the force acting on both the bodies is same, why does the apple fall and Earth does not move up? force is same, isn't it? Then why the Earth is not moving up? Go ahead, pause and think. The reason is because Earth has too much mass. The acceleration would be different. So acceleration of apple. So acceleration, acceleration of apple would be force over, this is writing wherever you want, just give me a second. So acceleration of the apple will be force over mass of apple, whereas acceleration of Earth, same force, but it will be divided by the capital M. So smaller mass, larger acceleration, bigger mass, less acceleration. So force is same, but acceleration and the movement is different because one of them is very heavy, it has a big mass. So the gravitational force of Earth is exactly same on both apple and the Earth. Now, what we can just write it as, now if the body is very close to Earth, okay, so in that case, okay, let me just tell you, the radius of Earth is 6,400 kilometers, okay, very high. So to what height an apple can be? 5 meters, 10 meters. So this h here is very small as compared to the radius of Earth. So you can basically assume that this r is equal to the radius of Earth. So if r is equal to radius of Earth, what can I find as the acceleration of, so if I'm just writing here, so my acceleration of apple would be gm over r square. So g is a constant, gravitational constant. M is the mass of Earth, which is constant wherever you go. The mass of Earth is not going to change. R is the radius of Earth, which is also constant. So this value, if the distances are very closer to Earth, this value here is something which you know as gravitational field strength or acceleration due to gravity. So this fairly remains constant if the distances are closer to Earth, and this also has a symbol which you know as small g, around 9.81 meters per second squared. So that is constant because depends on capital G, capital M, capital R. If you're talking about satellites or the moon, then obviously the body is way far away from the surface of Earth. In that case, your gravity is not constant. So your gravity kind of remains constant if the body is closer to the surface of Earth. So if I try to find out a relation, so if I'm just writing relationship here as G equals capital G M over R square, where R is the distance from the center of the Earth to the body. Okay, now here the mass of this body is of no significance. So this M here is the mass of Earth because it depends on the mass of Earth. If you calculate the force on the body, okay, so you can calculate it as M into acceleration, and the acceleration here is this. So you can just write M gm over r square. This is how Newton also calculated. This is gmm over r square. It's the same thing. So what you just need to let's just understand. So what I'm trying to say here is that the acceleration due to gravity is dependent only the mass of that planet or the star. So if a star has a bigger mass, radius is same, it'll have more gravity, more acceleration due to gravity. If it has a smaller radius, same mass, again the acceleration due to gravity would be higher. So acceleration due to gravity is proportional to mass of, I'm just writing planet, and or the star whose gravity you're trying to calculate. And of course it is inversely proportional to the radius square of the planet. Again, r is the radius of the planet. Okay, now let's just do some questions. Go ahead, pause and try to do it yourself. Once you've done that, you know what I'm talking about. F is G. G is universal gravitational constant. R is the distance between the two bodies of mass capital M and small m. Every time, pause and do it. Two masses attract each other. So because we're doing this topic as for the first time, I told you whenever you do a topic for the first time, always make a diagram. So two masses, M and small m, attract each other with force. Fine. So the distance between their centers is doubled. So if you double the distance, obviously the force is going to get weaker. But how much weaker? For that, we need to know the formula. So we know that force is inversely proportional to square of the distance because the mass is not being changed. So now this doubles. So I'm just right here, R doubles. So then force will become 1/4. So this is new force will become 1/4 of the original. Very typical multiple choice question. Two spheres attract each other. Again, I'm making the diagram. Two spheres, I have an obligation because you're trying to learn. So again, you also have the same obligation towards your brain. Don't stress it out. Make the diagram. Same force F. Now mass is triple. Let's say one mass is triple. So this becomes 3 times. Okay. So mass nu. Now we know that force is proportional to product of the masses. Now only one of them is tripled. So obviously now the force would be tripled. That's it. So 3 times the original force. One object mass is doubled, so m, another at small m, and the distance is, let's say, r. Now this is doubled, so I'm just going to make 2m, and the distance is tripled. So I'm going to write it here. So this is m, and the distance becomes 3r. So the force here is G. If you are one of those who think that your maths is not that good, go ahead, write it out. So here, my new force then will be Fn, will be G was a mass 2m times, the other one remains same, and this becomes the square of the distance. Okay, so you can see what factor I'm getting is a 2/9. So this becomes 2/9 times the original force. That's it. Why the force of gravitational force against distance is not a straight line? How can it be a straight line? What's my formula? My formula is this. So if my F is inversely proportional to r squared, every time I change my distance, let's just understand this. If my r is 1, then if my r is 2, then I'm writing 3 and 4 and 5 and so on. So the force is inversely proportional to r squared. So this becomes 2, this becomes 1/4. This becomes 3, this becomes 1/9. So this graph is something like this. So it cannot be a straight line because it's inversely proportional to r squared. Why is it difficult to measure the gravitational force between two ordinary objects in school lab? All right, now that's a good question. So if I have, let's say, one of my students, I'm not going to name one of you. I want to, but don't. I'm not going to do that. So one of my students has a mass of 60 kg, another one has a mass of 50 kg, and I keep them very, very close, so close. Yeah, let's just take it as, let's say, 0.1 meter. Not possible, but I'm just trying to do. So very close. Now tell me, what would be the value of the force between them? So G and 60 and 50 divided by 0.1 squared. Okay, so I get around 6.5, so 33,000 divided by 0. Should use calculator, times. Now this G is C, 6.67 10 to the power minus 11. Now can you imagine 10 to the power minus 11? Just plug it in the calculator, you're going to get 0.00000 and so on. So see, it's already so less that you can't measure it. We do not have that kind of Newton meters who have that high resolution, so it cannot be measured. Now what's the answer? Because the masses are very less.